Okay, 10.2. So in 10.1, we looked at the area under a curve, and now in 10.2, we're going to look at the area between two curves. So look at this lovely diagram we got here. We've got a lower curve. Down here, this is my lower curve, or lower boundary. And then I have an upper curve, or upper boundary. And I'm looking at it through the interval from A to B. So between the upper curve and the lower curve, we end up making ourselves a little section of area denoted with that big R. Okay, so between the interval of A to B, we could say that F2 at X is greater than F1 of X because it's above it, right? And so that's just defining who's upper and who's lower. And it's upper for the entire region of R, okay? And so what we can say from our work in 10.1 is that A of B, B being that right boundary guy, is equal to the area of the upper function between, so this is the tricky part, between, remember area under the curve goes up until the x-axis. So between my curve and the x-axis, that's going to be this part. Okay, that's that first part of the integral. And then minus the area between A to B of f minus 1 of x. So notice how this part, okay, so between my lower boundary and the x-axis, because that's what area under a curve means, okay, remember that this area here is going to come out as a negative value. Okay, just remember, because we're below the x-axis, that's going to come out as a negative value. So we're ending up with a subtract, and then this is a negative value. So what does that actually end up doing? So think about this. When this question below here says, does the above formula account for the fact that the area between the x-axis and my lower boundary would actually be negative? Yes, that's what this negative sign is all about. Let's say that the area of the green region is 6 and the area of the purple region is, I don't know, -2. Who knows what they are? Then if I am subtracting a negative value, I end up with a positive value and I get my area. This is the same as what we were doing at the end of that 10.1 lesson, where we were saying, oh, but the area underneath is a negative. So if I have to do that, I have to do the absolute value of that number in order to get my positive value. So my formula makes it so that I don't have to deal with this absolute anymore because it gives me this subtract. Okay, so yes, it does allow for me to not have to worry about who's above and below. That's taken care of. Okay, another way to think about this formula, okay, so we could take the integral of the upper region and the lower regions, like split it into two pieces, or we could actually use our properties of integrals and subtract the two functions first. Okay, so this is using my properties of integrals back in 9.1. If you wanted to go look back in the notes, and make one function first, and then you only have to integrate one function. Instead of having, in this method over here, you have to integrate it twice. But here, if we go upper minus lower and make our function first, then we only have to integrate the one. It's a little less work. I like this. This is kind of my preference. This is the one I'll probably do in the notes. Okay? All right, so to find our area between two curves, we need to do a checklist of things. We need to identify our upper and lower boundaries, who is above, who is below. We need to divide into subintervals if necessary. So what happens if they cross over at some point? Okay, so we're upper for this interval, let's say from A to B, and then all of a sudden we go lower from B to C. Okay, so then you're going to need to find intersection points and do it in chunks. Okay, so then I like to subtract the two original functions, upper minus lower. This is me using this second property of integrals method. Integrate or take the antiderivative of that function, and then evaluate at the left and right boundaries, subtract the resulting values. And don't forget to write units squared. Okay, so don't forget your units. Don't forget units, because we are calculating area. All right, let's try one. Example 1, determine the area between y equals x squared plus 1 and y equals x. So notice we now have two functions to work with and a boundary. So from x equals 1 to x equals 3. So it's going to be really important that we draw ourselves pictures. Okay, so y equals x squared plus 1 is a parabola that has vertically translated 1 unit up. That's a terrible parabola, but you know what I'm doing. And then y equals x will never intersect with that parabola. And we are going from the boundary x equals 1, okay, to x equals 3. So here we go. Beautiful. Lovely diagram, you know, and if we were really great about it all, we would label who is who, because Malmstrom likes that. And if we had intersections between the two graphs, we would also label those intersection points. This one we get off easy. All right, let's decide who is who. Okay, so my upper function is x squared plus 1, my parabola, and my lower is y equals x. Okay, I guess I should really have that was equal to y. That would be better, but doesn't really matter. Okay, so now I'm going to do upper minus lower. Okay, upper minus lower. So x squared plus 1 in brackets, subtract lower, which is just x. So what do we get? We get x squared minus x plus 1. Can you deal with the fact that I reordered things as I subtracted? Hopefully we're awake enough to do that. Okay, so this is the function here that I want to take the antiderivative of. Okay, we could have done the integral of x squared plus 1, subtract the integral of x. We could have done that, but I like to make the function first, and I only have to integrate once. Okay, so that means my area to my right boundary 3 is equal to the integral from who was the left boundary 1 to the right boundary 3 of my function x squared minus x plus 1 in terms of x. So now I get to do my calculus. I'm going to take the antiderivative of this. So the antiderivative of x squared is 1/3 x cubed. The antiderivative of x is 1/2 x squared, plus the antiderivative of 1 is x. And we are going to evaluate that from 1 to 3 and see what we get. So we now have 1/3 3 cubed minus 1/2 3 squared plus 3. All of that should have an equal sign out there. Subtract. And now I plug in the 1. 1/3 1 cubed minus 1/2 1 squared. That's a cubed back there. Plus 1. And figure out these numbers. So we get that this first number comes out to 15 on 2. Subtract the second number is 15 on 6. And what do we get? All of that is 20 on 3 units squared. So you could have like a little therefore statement at the end. Therefore, the area would be equal to 20 on 3 units squared. That's just using proper notation. Okay, well done. I'm going to pause the video here And I'm going to let you think about drawing this picture out. I just don't think I'm going to get through it all in the next video, and I don't want to rush it. So think about what this would look like in its setup. Find the total area enclosed by a cubic with a line. Okay, and it doesn't give me an A and a B. So I just want you to think about that for a minute. Maybe draw out the picture, see what it looks like. Not maybe, please do. Please draw out the picture before you start the next video and see what you have determined as what those intervals are, because it didn't give me an A and a B. Okay, see you soon.